Hello. In this session of Metrology and Instrumentation, we are discussing on strain gauges and load cell. In the first part, there is strain gauge, and the second part, there are load cells. We discuss about various kinds of load cell in the second part. Let us quickly go to the concept strain gauges. Strain gauges are devices used to measure strain. That means the linear deformation over a gauge length. These are generally fitted on free surfaces. When the surfaces undergoes a strain, the strain will be transferred to the strain gauge. They sense the change in length, magnify and indicate it in some or other form. Strain gauges are the prominent tools used in stress analysis. Measurement of strain has applications in measuring forces, pressure, acceleration, torque, etc. There are various kinds of strain gauges based on the mechanism by which the strain is sensed. We have mechanical strain gauge by which mechanical movements are used to sense the strain. Electrical strain gauges are using electrical principles to sense a strain. Like that, we have optical strain gauge, pneumatic strain gauges, acoustic strain gauges, etc. In the second part, we will be discussing on load cells. Load cell is a force transducer that will convert the applied force, like such as tension, compression, pressure or torque, into a signal that can be measured and standardized. As the force applied to a load cell increases, the signal will also change accordingly. There are many common kinds of load cell used in applications such as strain gauge load cells, piezoelectric, hydraulic and pneumatic cells. In this session of part 1, we are looking on strain gauge only on electrical resistance type of strain gauge. Let us quickly go to the concept of utilizing strain gauge for measurement. Let us look into this diagram. This is a strain gauge. That means strain gauge consists of a resistance wire, and the wire will be kept in a particular form. In this diagram, the wire is kept in this kind of zigzag kind of form, and this strain element, this is called a strain element, that will be fitted on a surface for which strain is to be measured, like this. Say this, what you see here, it is a rod, a metallic rod. On that a strain gauge is attached. You can see the resistance elements on that, and you can see that these are leads. These leads are connected to an external circuit where, when there is a strain happens to this, corresponding to strain, a voltage will be generated. Let us see how the voltage will be generated when there is a change in change in length. Strain, we know that it is the change in length with the original length. We have the principal resistance equation. R is equal to rho L by A, where rho is the resistivity, L is the length of the resistor, A is the cross-sectional area of the resistor. Based on this principle, we know that when there is a change in length happens for this, obviously there will be a change in resistance will also be happening. That means the change in resistance to the original resistance will be proportional to the change in length to the original length. That means the changing resistance to the original resistance is proportional to the strain. That is, change in length to this is a strain. So when we remove the proportionality constant, we can say that it is G is the gauge factor. So change in resistance is proportional to strain, and the gauge factor is the constant that depends on the material property and the arrangement. That means when this strain element, that is this element, when it is subjected to a strain in this direction, this direction, then the element will elongate in this direction. All these elements will elongate in this direction. Thereby change in length happens for the entire length of this element. So that change in length will reflect in change in resistance. If this resistance element is a part of an electrical circuit, typically it will be a part of a Wheatstone bridge, where there will be 4 resistance in a bridge, and all the 4 resistances will be of same resistance and same property. So when there is a change in resistance happens to one of the strain gauges or one of the resistance in the Wheatstone bridge, there will be an unbalance happens for the bridge that will cause a voltage output from the bridge. So the voltage output is an indication of the strain that is happening to the strain gauge. We have to remember a very important property of the strain gauge that is called as directional property, that you see here, directional property. You know, when the strain gauge is attached on this tube is going in this direction, say the force is applied on this tube on this direction, so that this strain gauge will have an elongation happening in this direction. That means there is a changing length happens, thereby the strain happening because of the force in this direction will be reflected to the change in strain, thereby change in voltage in the external circuit. So corresponding the force, we can sense the strain on this by using this arrangement. Now you take and imagine a condition where instead of placing this strain gauge in this direction, if I am placing the strain gauge in this direction like this, so here when the force is applied in this direction, in fact it will just stretch rather than elongate. That means for a particular strain or force happening and the strain happening in this direction, there is no appreciable change in length happens for the strain gauge if it is applied, placed in the orthogonal direction compared to the original direction. That means in order to sense strain in a particular direction, the strain gauge need to be oriented along the direction itself, and if a strain gauge is oriented perpendicular to the direction, the strain will not be sensed. So this principle is used in many cases that we will see later. That means the strain gauges are to be oriented properly for measurement of strain in a particular direction. Let us try to see the classification of electrical resistance strain gauges. Let us classify strain gauges into majorly two categories. We can have one more category, subcategory like this. The categories are bonded type strain gauge. The meaning is that we know that the strain gauge will have a resistance element. The resistance element is bonded to the surface whose strain is to be measured. That means the resistance element such as wire may be bonded on a flexible surface. Here we have two examples of bonded type strain gauge. One is wire type, another one is a foil type. In wire type, the wire is bonded to a flexible surface like this. What you see is like a white background. It can be a flexible membrane or flexible plastic or any non-conductive material. On that it is placed, it's pasted on this. Such a type of strain gauge is called as a wire bonded strain gauges. Here is another arrangement where there is a foil rather than wire. It is a foil that is cut into a particular shape and that is pasted on a base. So this is called as a foil type. Both are bonded type because the resistance element is bonded to the surface of the strain to be measured. For measurement of strain, this particular non-conductive material along with the strain will be pasted on the surface of the object to be sensed, as we have seen in the previous case here like this. So this is a strain gauge, that is this is a flexible membrane, the strain that is pasted on this. Now another category is unbonded type strain gauge. Obviously the resistance element is not bonded to the surface. Instead, the resistance element is linked to certain points on the surface. Let us see the exact description based on this particular diagram. Say this is a movable frame, this is a fixed frame, and on the fixed frame there are few points like 1, 2, 3, 4 points, and there are 2 points on the movable frame here, 1, 2, and another points here, 3 and 4 here, say. Now these 2 points are connected by means of a wire. These are connected by means of a wire like that. Other 2 points are also connected by means of wire. These wires are resistance elements, and these 4 wires are part of a Wheatstone bridge as you see here. So the resistance what you see here are these resistance wires. Now these wires are now in the preloaded condition. Imagine that this particular outer frame is moving in one direction because of some force in this direction. Now what happens is these 2 wires will stretch in this direction, whereas this will move in this direction, stretch in this direction, and this will also have a change in length for these 2 resistance. So these 4 resistance being part of the Wheatstone bridge when there is a strain happens because of the force, these will result in change in voltage output of this Wheatstone bridge. So this is the way by which we use unbounded strain gauges for measuring strain. The meaning is that instead of conducting the wire directly on the surface, these wires are connected to certain points only on the objects where the relative movement between the objects can be sensed. So separate objects when it is undergoing strain with reference to another, this kind of strain gauges can also be used. Semiconductor type of strain gauge is another strain gauge where they use typically piezo resistive type. Piezo means pressure, resistive means resistance. When pressure applied or the strain applied, then resistance will change for certain elements. Typical material used for the semiconductor type of strain gauges are boron doped silicon or germanium. These semiconductor type strain gauges are more sensitive to temperature and more sensitive to strain. So they are used for very accurate and critical applications. These are highly resistant to temperature also. The typical materials that are used for conventional strain gauges are constantan, nichrome, platinum, tungsten alloy and all. When we use a material for strain gauge, it is very important that the resistance per unit length of the material should be constant for the entire length. Then only we can take the change in resistance as an indication of change in strain that is happening for the object. Let us see one application to see how strain gauges can be used for measuring strain or force. To explain this concept, I'll use an example of strain gauge dynamometer. Dynamometer is a device that is meant for sensing force, and in this particular example, this dynamometer is used for sensing the force that is happening during machining. It's a very familiar case of turning process where a single point cutting tool is used to machine this material. You know that there will be three forces in the case of oblique cutting process. The cutting force that is happening in this direction, there is a radial force and there is axial force in this direction. Now if you want to sense a the cutting force, the major force in this direction, as we have seen earlier, if there is a force happening like this in this direction, force will be experienced on this particular cutting tool, and there will be one strain gauge attached to this membrane inside the dynamometer. So when there is a force here, that will cause a stretching of this particular element, and that eventually will result in stretching of the strain gauge. So that strain gauge change, the change in strain happening for this element is an indication of the force that is happening on this. That means if you want to sense force in this direction, there should be a strain gauge aligned inside the element, inside the dynamometer in this direction. Again, if there is a force to be sensed in this direction, there should be another strain gauge attached in this direction in order to sense the force in the direction. So for three forces, there should be three devoted strain gauges inside the dynamometer, because we know that strain gauges are direction sensitive. Now let us see how this is used in a Wheatstone bridge. We have a demonstration here. This is a Wheatstone bridge where we have four resistors. In this diagram only two resistances are shown in the form of strain gauge. In fact, all the four resistors are having the same resistance as that of the strain gauge initially. Now this particular arrangement shows the use of strain gauges with temperature compensation. Temperature compensation means we know that the resistance change in a strain gauge can also happen because of change in temperature. It is not just even because of the applied force, but we are interested only in the force applied, not because of not the effect of temperature. For that, we use another technique here. The directional property of strain gauge is used here to compensate for the temperature. I will explain based on this. In this diagram, this is a strain gauge that is used for measurement, that is a stressed strain gauge. This is another strain gauge that is unstressed, that is not used for strain measurement. Instead, it is used for temperature compensation. How it is used, this particular strain gauge will be used in a particular direction along which we expect a force, and on the same member another strain gauge will also, this strain gauge will also be placed in the orthogonal direction. The advantage is that the strain gauge used in along the direction of force and the strain gauge used in orthogonal to that, both will be subjected to the same temperature, but the orthogonal directionally placed strain gauge will not be influenced by the strain, but the other initial one will be subjected to strain. That means the effect of temperature on both will be same, and if at all there is a change in voltage that happens for the system, and that change in voltage is not because of the change in temperature, because these two are subject to temperature, and it is because of only the force that is applied in that particular direction. Because the Wheatstone bridge utilizes the principle, the ratio of resistance, that is R1 and R2 will be equal to the ratio of R3 and R4. If you know that if R2 and R4 both are of same resistance, even changing resistance because of temperature, it will not affect the ratio. So that is a way by which strain gauges are used for temperature compensation. Strain gauges have got certain properties, like though I have explained the use of strain gauge in the case of machining, we know that machining is subjected to dynamic force, that is the force happening at the tip of the cutting tool will be keep on varying with reference to time. It's a dynamic loading condition. In fact, strain gauge is not recommended for dynamic condition because it has got very slow response to dynamic loading. Strain gauges are useful for static loading, such as the case of taking weight. You take the case of mass measurement when you in the case of a mass balance where you want to measure the weight of, say, a rice or something like that in the grocery shop and all. There we can use strain gauge because the load once you keep it is static. It is not going to vary. Similarly, if the load happening in the case of the weighing bridge, you might have seen the huge lorries are taken to weighing bridges where there will be strain gauge. The strain gauge, again, it is used for measuring the static load because the load is not varying during the measurement process. So any case where static loading is seen, strain gauge is preferred rather than dynamic loading conditions. Then effect of temperature will be there. We have seen how the effect of temperature can be nullified, and compared to other strain gauge it is cheaper, so it is very widely used. Now it is time for a review. Can you verify if you can describe the working principle of electrical resistance strain gauge? Can you derive an expression for gauge factor for strain gauge? Can you classify electrical strain gauges, bonded, unbonded, semiconductor, etc.? Can you explain the method of using strain gauge for temperature compensation? We have seen the orthogonal property of the strain gauge for temperature compensation. Please review the content of strain gauge now. We will see the load cell in the part number 2. Bye.